Okay, and happy to introduce Professor Cora Dvorkin talking about astrophysical probes of dark matter.
Thank you very much. So yes, I'm Cora Dvorkin. I'm an associate professor at the physics department here at Harvard, and I do research on theoretical cosmology. So a little background about myself. I was born and raised in Argentina. I did my undergraduate in physics at the University of Buenos Aires. Then I came to the US to do my PhD in physics at the University of Chicago, where I did research in cosmology. And after that, I went to the Institute for Advanced Study in Princeton for a postdoc. And when I finished that, I started my postdoc at the Center for Astrophysics here at Harvard. And it was supposed to last for 4 years, but after the first year, I came to the physics department as faculty, and I have been here for the last 6 years. So I'm a theoretical cosmologist. Cosmologists study the origin, the evolution, and the fate of the universe, just small tasks. From a very long time, this was a very speculative field. We had very little data. But in the last 3 decades, this changed dramatically, and this is because of all the data we have collected from satellites and telescopes all over the world. Cosmologists are like archaeologists trying to understand our past to better understand the composition of the universe and the fate of it. So let me start this story in 1929 with the astronomer Edwin Hubble that I'm showing here, who showed that the further away a galaxy is, the more rapidly it's moving away from us. In other words, he showed that the universe was expanding. You can see here in red, you see my cursor? Yeah. In red, you can see Hubble's original diagram, which then got extended with better measurements. So, but you can see here that the further away a galaxy is, the more rapidly it's moving away from us. So he concluded that the universe was expanding, is expanding. So what does this mean? Well, it means that distant galaxies are receding. The more distant the galaxies, the faster the recession. Because space is expanding. So you can think of galaxies as racing in a racing loaf of racing bread. I like to think about them in that way. And whichever galaxy or racing you're in, the others will appear to be moving away from you. So the farther away they are, the faster they appear to move, because there is more space, or if you want, there is more dough between distant objects. Another aspect of this is that light is emitted by objects at certain known wavelengths. And so as light travels towards us, the wavelengths of light are stretched because of the expansion of space. And we call this redshift. And it allows us to measure the motion away from us. We measure the stretching of light. So we learn that the universe started as a very hot and dense plasma of particles. This was like a very hot soup of electrons and protons, and this plasma was oscillating. The particles were being pulled together because of gravity, and the light was bouncing around. And the photons move and they exert pressure, so the particles decompress. So the early universe was oscillating in and out the potential wells. And we call these acoustic oscillations, and I like to think about it as a cosmic symphony, because these are pressure waves. You probably discussed this. I saw that Professor Daniel Eisenstein came to Physics 95 to give a talk. So you probably discussed this cosmic symphony, these acoustic oscillations with him. So as the universe expands, it cools down, and eventually protons and electrons could combine and form neutral hydrogen in a period that we know as recombination. When that happens, the photons don't interact with the electrons anymore. And these photons come toward us carrying messages from the very early universe until they enter our detectors. And this light has been coming toward us for over 13.8 billion years. So how do we study our past? Well, the key here is that we can use light to study our past, and that light doesn't change its speed, even if the universe is expanding. The speed of light is constant, as you probably know from special relativity. So when we look at stars, for example, light can take many light years to reach the Earth. And when we look at the distant universe, we see that the universe, when we look at the distant universe, we see how the universe was in the past. So the further away we look at, the more in the past we can go. And so cosmologists use the properties of this light to understand the physics of the early universe and the composition of the universe as a whole. In particular, when this light from the Big Bang comes to us, it reaches us at microwave frequencies. This is why it is called the cosmic microwave background. The particles of light, let me start this video. The particles of light, the photons, shown in blue here, couldn't go far at the beginning without colliding with an electron. And as the universe cooled, protons and electrons form hydrogen atoms, and the light was free to travel through the dark ages where there were no stars, past the formation of the first stars. And as the universe expanded, photons changed their color, as you can see here, and the photons traveled through 13.8 billion years before reaching our detectors. There's the photon traveling, changing colors from time to time, bumping into a free electron. We can see there are galaxies already. And finally, the photons reach our detectors. So let me move here. A difference between us cosmologists and other fields in physics is that we cannot go back to the beginning of the universe and rerun our experiment, changing its conditions. So in that sense, I say that we are like detectives looking for clues in this ancient light. We cannot restart the universe, but we look for clues, try to understand our model better, and make predictions for new observables and test our predictions. So from different measurements of the statistical properties of the light that comes to us from the Big Bang, the cosmic microwave background, and of the structures in the universe, we have learned that we have a standard model of cosmology that explains the universe beautifully. It is known as lambda CDM. We basically have a homogeneous background, and we measure the parameters of this background to percent level precision. We know that we have approximately 5% of ordinary matter, which is matter that makes you, me, the stars, etc. And the rest is in the form of dark energy, which is what we call the source responsible for the accelerated expansion of the universe that we observe today, and dark matter, which we will talk about later today. So there are two other parameters that describe the initial conditions of the universe, and the last one describes the first stars. So this is a beautiful model that fits the universe at large scales with only 6 parameters. And we measure these parameters very well. However, we still have very important unanswered questions. What is the physics that sees the first structures in the universe? What is the lambda in our lambda CDM standard model of cosmology? And by this, I mean, what is the source of the accelerated expansion of the universe? And what is the CDM in lambda CDM? What is the nature of dark matter? And so for the rest of the talk, I will be focusing on this question, which is the question that we try to answer with my research group here at Harvard. What is the nature of dark matter? And dark matter comprises about 84% of the matter in the universe. 84%, and we still don't know what it is. And today I will tell you how we are using astrophysical observations to tackle this question. So let me talk a little bit about dark matter now. There is overwhelming evidence for dark matter at different scales, from galactic scales to the cosmic microwave background. And the first hints of dark matter were there from the 1930s, but the measurements weren't good enough and nobody really believed them. It wasn't until the 1970s when the measurements became more precise, and this was really due to the pioneering work by Vera Rubin that you can see here. At the time, she chose to work on this topic because not many people were working on it, and she thought it would give her more freedom. And she made observations that confused people ever since. Vera Rubin measured the rotational speed of stars, you can see here, as a function of distance to the galactic center through the broadening of the spectral lines. And so here I'm showing you a plot of the velocity of stars or hydrogen gas as a function of distance to the galactic center. So if the only matter in the galaxy were the visible matter, once we get to about 5 kiloparsecs at the outskirts of the galaxy, we should see that when we apply the laws of Newtonian mechanics, the velocity should decrease with the distance. We should see something like this dashed line over here. In fact, this is not what we see. We see that the velocity is almost constant. And Vera Rubin presented her first result on this topic in an influential paper in 1980. So what Vera Rubin saw is that there is actually more stuff that we don't see around the galaxy. This slide means to summarize what we know about dark matter. There is a galaxy in the center, and we think around us there is a halo of dark matter. The visible part is actually about 10 times smaller than the rest. And we think that billions of dark matter particles must pass through us each second. Most pass unhindered, but about 10 to 100 particles hit a nucleus in our body in a year. Another piece of evidence for dark matter comes from the cosmic microwave background, or CMB, the afterglow that I was talking about from the Big Bang. And this is a figure that I like from my PhD advisor, Wayne Hu, that shows what happens when you change the fraction of matter in the universe. What happens to the acoustic peaks in the CMB. This slide that I'm not going to talk a lot about today because I don't have time, but this slide was first discovered by Penzias and Wilson. Wilson is actually here at the CFA. It was discovered in 1964. They did so by cooling their detectors with liquid helium to minus 269 Celsius, only 3 Kelvin above absolute zero. And many different satellites and telescopes have measured the CMB since then. The first of these satellites, known as COBE, the Cosmic Background Explorer, found that the CMB has fluctuations around this value of 1 part in 100,000, which is basically, I like to say, the width of a fingernail in a kilometer. Those are the fluctuations of the CMB around its absolute 2.7 Kelvin or almost 3 Kelvin temperature. So here you can see in these peaks the square temperature fluctuations as a function of angular size in the sky. Okay, here I'm showing you large angular separations, and here I'm showing you small angular separations. And these are the square temperature fluctuations. So these are the fluctuations coming from the early universe that I was talking about before. And the relative amplitude of the peaks tell us how much dark matter should be there. When we decrease the dark matter, the fluid sees no gravitational potential that pulls back, so the amplitude of the oscillation goes up, as you can see here. And different types of dark matter scenarios leave imprints in the CMB acoustic peaks. In fact, we suggested to look for those in a proposed next generation CMB experiment called CMB Stage 4 that started being funded by DOE a couple of years ago. So you may ask, what do we know about the nature of dark matter? Well, we know that the effect of dark matter appears in the CMB, so it must be old. We say that it is cold, meaning that it must have been non-relativistic to form small-scale cosmological structure. Otherwise, it would never cluster. This is why we call the standard scenario the cold dark matter scenario. And we also know that it can't have much interaction with light because we don't see it. So we don't know what dark matter is. What we know for sure is that it interacts with gravity. And with my research group here at Harvard, we study new ways in which we can extract information from astrophysical datasets to understand the nature of dark matter. And since I only have 30 minutes, and now even less, I will try to give you a glimpse of our work at small scales in the next few slides. So in the cold dark matter scenario, we expect a high abundance of substructure in dark matter halos. This can be seen in the left in this figure over here that I took from one of Andrei Kravtsov's papers. Andrei Kravtsov is a professor at the University of Chicago, where we see the predicted dark matter density for a Milky Way-sized halo from a high-resolution N-body simulation. And we can see from here that there is a lot of structure within the halo. And one of the things we have been analyzing with my group is how to tie these structures to dark matter, to different dark matter theories. Moreover, we actually know that these structures exist because we have actually observed them. Here on the right, I'm showing you a map from last year from the Dark Energy Survey, or DES collaboration, of observed Milky Way satellite galaxies, meaning small galaxies that are bound to the Milky Way. As an example of the effect of different dark matter models on subgalactic scales, I'm showing here two different projected dark matter densities. One coming from an embodied simulation in a cold dark matter, or CDM scenario on the left, and on the right here, I show a simulation with the same initial condition, but including some exotic dark matter microphysics, not necessarily under the cold dark matter scenario. You can see here already by eye that there is a lot more structure in the CDM scenario compared to the exotic dark matter physics scenario. And this is just an example to illustrate the fact that exotic dark matter physics can lead to interesting phenomenology that is observably different from CDM on these scales. We are probing dark matter fluctuations on small scales, and by this I mean kiloparsec scales. Large scales are, hundreds of megaparsecs in cosmology. So we are probing dark matter fluctuations on small scales to falsify or corroborate the cold dark matter paradigm. And our tool to understand how to map the distribution of dark matter on small scales in halos of galaxies is known as gravitational lensing. Let me give you a review in one slide of gravitational lensing. So in general relativity, gravity will distort space-time, as you probably saw on Monday, a brief review of general relativity. So the presence of a massive structure like a galaxy will bend the light coming toward us, and we will use the effect to look for dark matter. Gravitational lensing is a prediction of the theory of general relativity. In contrast to this, in special relativity, space-time is flat. So here we have a background source at some faraway distance, which will be a galaxy in our case, and there will be a foreground galaxy that deflects the light because of gravity. And so from our perspective, we are here in these telescopes, we will see arcs. And the idea will be to use these images to see if the lensing galaxy, the one over here, is clumpy or smooth. And so the idea is that substructure in the halos will locally perturb lens images. So by looking at the residual between the image predicted by modeling the galaxy lens as a smooth mass and what is actually observed, we can infer the presence of subhalos. And the advantage relative to other methods for detecting dark matter is that we do not need to assume a specific coupling between the standard model and the dark matter, in contrast to what is done, for example, in direct and indirect detection experiments or colliders. And so in this sense, I like to say that we are model independent. Furthermore, the lowest mass subhalos are largely devoid of stars. So detecting them with a gravitational technique is the only possibility, since these subhalos cannot be seen directly. We cannot see these subhalos directly. So the only possibility that we have is to detect them via a gravitational technique. So we won't have the same picture as before, but now we will add a subhalo, or perhaps more than one. You can see here, this is what I call substructure, in the halo of the lens galaxy. And we will look for a small deflection as the light from this source crosses the lens. So we will look for these arcs. We will look to see if they're clumpy or smooth to detect small subhalos. And the idea is that by detecting these subhalos and counting them, we can discern between different dark matter theories. So with my group, we have done work in this arena following two different but complementary approaches. The first approach is what I call a direct detection approach, where our goal is to resolve individual, more massive perturbers, and from there infer their properties. The second approach is a statistical detection approach, or what I call indirect detection here, where we want to marginalize over individual subhalo properties to learn about the subhalo population characteristics. And so here we exploit the expectation that we have a huge population of these very low mass subhalos to try to statistically detect their collective perturbation on images. I won't have time to talk about this approach today. Ask me later if you're interested. But let me say a few words before I run out of time about the direct detection approach. So direct detection of substructure is computationally very expensive, taking months to analyze each system, and most of the time one gets null detections. In direct detection approaches, one has to model the smooth lens, or what we call the macro model, independently before trying to look for subhalos, and lens modeling is not straightforward. But so far the pool of lens images has been small. However, in the next few years, we expect tens of thousands of these lenses to become available for this type of science through the Vera Rubin Observatory, for example, formerly known as LSST, and other experiments, in addition to further follow-ups by the Hubble Space Telescope or the Extremely Large Telescope, etc., etc. And in fact, there are already many recently discovered by the Dark Energy Survey that are waiting for follow-ups. So this is great, since the vast increase in sample sizes that we expect will provide much stronger constraints on dark matter. But obviously, it is unsustainable to take months to analyze each system if we are expecting to have tens of thousands of them. So what motivated us, together with my former PhD student, Ana Díaz Rivero, was the following question. Can we automate a procedure like direct detection using convolutional neural networks, making this process much faster and avoiding the step of macro modeling? So given the large number of lenses expected, we decided to develop a different approach to find substructure, which will be more suited for this new era of large data sets. We used a convolutional neural network to analyze strong lens images and to infer whether images had substructure or didn't have any. And we show that small-scale substructure can be inferred directly from astrophysical images by using convolutional neural networks without any intermediate modeling of the lens galaxy, taking much less than a second to analyze a system, of course, once the network is trained, versus months of analysis in traditional analysis. We have done more work on this later on, together with a postdoc working at my group, WNS Dec, where we use a different type of technique known as image segmentation. This is essentially the program of taking an image, or perhaps you can think of a frame in a video, and trying to understand what are the individual components that make up this image. Well, the network was trained only on images with a single strong lens and a single low mass subhalo close to the lens image. We saw that the network is able to detect subhalos that are far from the lens image, as well as the mass and location of additional subhalos. Furthermore, we show that the network is also capable of identifying, for example, two different main lenses. So by learning the fundamental physics giving rise to these images, the network is able to generalize very well to images that look very different from the training samples, but are nevertheless governed by the same principles. In fact, I became so excited about using machine learning techniques in my research that I joined forces with colleagues in various disciplines of physics and computer science at MIT, Harvard, Northeastern, and Tufts. And we started last year, in the middle of the pandemic, a new NSF-funded AI center that we call IFI, which stands for Institute for Artificial Intelligence and Fundamental Interactions, where I serve as the Harvard representative at the Institute board. And so it is part of my role to advertise it and tell you that our colloquia are on Fridays at 2 p.m. Eastern Time, and everyone is welcome to attend those. You can go to this link that I'm showing here and get more information about the research done, and also you can look at previous talks if you're interested. So let me take 2 more slides if I have time, if I can. Yeah. So we just saw ways of detecting subhalos within the lensing galaxy. However, the distances involved in strong lensing systems are vast, and we expect the relevant volume to contain line-of-sight halos that are not necessarily associated with the main lens. And recently, in work carried out by my group, in particular, I want to emphasize 2 of my graduate students, Chan Sengul and Arthur Sang, and collaborators at Berkeley, we developed a formalism to calculate the effect of line-of-sight halos as an effective surface mass density field. And now, instead of having a single lens plane at some redshifts, we can have any number of lens planes corresponding to the line-of-sight halos. And instead of using the vanilla lens equation, we now use a recursive lens equation, which couples the angular deflections of successive lens planes. And so by assuming that the perturbations due to the line-of-sight halos are small, we show that they can be projected onto the main lens plane as effective subhalos. And we tested our formalism by simulating lensing systems using the full multi-plane lens equation and found excellent agreement with our analytical predictions. And we showed also that we generally expect to have more line-of-sight halos than subhalos for typical lensing configurations, which is not surprising, given the vast distances that we're talking about. In terms of current data, let me advertise a paper that should be coming tomorrow. We are reanalyzing systems that were previously claimed as subhalos in the literature, and our current analysis indicates that it is likely that a number of them are actually halos along the line of sight. Here is one such example that was claimed to be a subhalo in a Nature paper. And these are our results from our likelihood analysis. And you can see that the system is indeed very likely to be a halo along the line of sight, as opposed to a subhalo, as it was claimed before. You can see the redshift or the distance to the main lens, and the distribution found for this perturber. Our analysis also indicates that this structure is more massive by more than an order of magnitude than the previous result, which is consistent, of course, with being further away. Okay, so in sum, we saw that the CMB and the large-scale structure of the universe encode a wealth of information about the nature of dark matter. And we also saw that important clues about dark matter physics lie on small scales. detections of dark subhalos via gravitational lensing, which is a prediction of general relativity, have great potential for revealing the particle nature of dark matter. And more generally, I would like you to take the following message home. This decade is bringing a wealth of new and complementary data sets, and we will continue to exploit their complementarity and look for new ways of extracting information, and we should be brightening the dark sector soon. So let's stay tuned for that. Thank you.
Thank you so much for such a wonderful talk. I'm going to open the floor to questions. If anybody wants to go ahead and unmute and ask a question. I also had a question to get us started off. You mentioned, I believe sort of quickly, that this model for dark matter doesn't need to agree with the standard model. Is that correct? I was curious about why that is.
Right. So by construction, the models agree pretty well with observations at large scales. So we know that cold dark matter scenario agrees very well with observations at large scales. However, small scales are more complex and are not as well understood. So there is room for having different dark matter scenarios. So the idea is to probe the fluctuations of dark matter at small scales to be able to discern between different dark matter scenarios.
Okay, got it. Thank you. Are there other questions? And feel free to go ahead and unmute.
I have a question that isn't super related to what you were talking about, but I was curious anyways. I was just wondering what you think about the like H0 and sigma 8 tensions, and I don't know whether you think that those are actually problems or if they'll be resolved somehow.
So the H0 tension taken at face value is now already what I would call a problem. It's a 4 to 5 sigma tension, and it seems to be very difficult to construct to make everything, to construct a new model that fits all the observations. However, it is possible that there is some new physics that is missing, and observations from direct measurements of supernovae and the inferred value of the Hubble constant coming from the early universe may agree with when you add new physics in the bag. If this is not solved with new physics, another possibility is that there is a systematic effect, either from the early universe observation side, from the CMB or the large scale structure, or from the supernovae measurements. So at the time, it's hard to tell what will exactly happen. In terms of sigma 8, the tension has a lower significance. So it is a problem, but not as major as H0. And it is also possible that we are not understanding well how to model nonlinearities in the data. So there could be new physics. There could be some modeling assumption that is broken in the measurements, but the need for new physics is less at the moment than the need for new physics, taking at face value the tension in the Hubble constant. There are many, many groups working on this, so hopefully I expect that we should find, an answer to this. in the next decade for sure.
Are there any other questions? We probably have time for one or two more.
What are some other things that you anticipate or expect to change, whether it's discoveries or, I don't know, agreed upon consensuses within the next decade, maybe like you said?
Yeah, that's a great question. So there is so much data coming in. We will be able to learn really a lot about the early universe from large-scale structure data. We will be able to make a lot of progress about the nature of dark matter, also measuring the small scales. You know, not only, I'm talking about the questions that I'm mostly interested in, but we will also be able to learn a lot about galaxy formation, about how stars form. There is a lot of data coming in the next years with the Vera Rubin Observatory, with new CMB experiments, the Simons Observatory, CMB stage 4, with DESI that is already taking data, with JWST, lots of experiments. And so we will have a lot of data, both from the cosmic microwave background and from what is called the large-scale structure of the universe. And you know, we will try to utilize this data in complementary ways to learn about the physics of the early universe, the composition of the universe. We will learn about neutrino masses also. With the gravitational lensing of the CMB, we will be able to put very tight constraints on the neutrino mass, the sum of the neutrino masses. And in fact, we expect these constraints to be so tight that we will be able to distinguish between the two hierarchies. So there will be a lot of progress in this coming decade. And with the measurements of polarization of the CMB, we will be able to either detect primordial gravitational waves through the B-mole polarization of the CMB, or if not, to rule out a large chunk of parameter space in models of inflation that try to explain the first fraction of the second after the Big Bang. Yeah, that's a great question. Thank you.
We should have time for one more if anyone wants to ask one final question. If not, if there's no other questions, then we can end things here. Thank you so much, Professor Dvorkin. Stop the recording.